For the next video in the learning rate series, we're going to take a look at learning rate schedules. So this is changing the learning rate over time instead of keeping it fixed throughout training. We'll have seen this formula before in a previous video, and this is how we update the parameters of a network using stochastic gradient descent. So the key hyperparameter for this formula is the learning rate, which is denoted by alpha, and this controls the step size that we're going to take to update the parameters once we found out the gradient. The alpha stays the same throughout training, and this will give us different profiles of the learning curve. We've seen these before in the previous video. And all of these curves assume that there's a constant learning rate throughout training. But we can see from the graph that the curve in green, for example, with a high learning rate, has better and quicker convergence at the beginning of training, but then has a limit to how far the loss can decrease. But if we had a lower learning rate, such as the one in red or blue, we can reach a lower loss, but it takes us longer to get there. So maybe we could combine learning rates and change from higher to lower over time to get benefits of both. And that's what we try and do with learning rate schedules. So a schedule just defines how we change the learning rate over time. So instead of having a fixed alpha, we change the alpha every iteration potentially. And this is denoted by alpha sub j, which is denoting the learning rate at iteration j. So schedules define how we change the learning rate over time, and they're specified for every epoch or iteration of training. So for MXNet, we'll see that the schedules are defined on the iteration basis rather than an epoch basis. And as mentioned before, we can use learning rate schedules to overcome the speed versus performance trade-off that we found with a fixed learning rate. So is this the same as adaptive methods, such as ADAM and ADAGRAD? Well, not quite. They're a little bit differently, and they differ in two different ways. So the firstly is that adaptive methods generally change the parameter-wise learning rates. So there's a separate learning rate for each parameter of the network. But here, when we're controlling the learning rate, we're just talking about a global learning rate for the optimizer. And secondly, the schedules are defined beforehand, and unlike adaptive methods, they don't take any feedback in terms of the size of the gradients and the size of the steps, for example. So it's a little bit different to the adaptive methods. So now let's take a look at how we can use learning rate schedules in MXNet. So we're going to start by importing all the packages that we need for MXNet, and we're going to define a plot schedule function. So this is going to help us visualize the learning rate schedules that we're going to use. So you'll notice that plot schedule function takes in a schedule, and it will run the first 1,500 iterations, and it will work out the learning rate for each of those iterations. So we have a specified amount of iterations we're going to pass through. We start at iteration 1 rather than 0. That's quite an important point to note. That's just the convention used for the learning rate schedules in MXNet. And then we loop through all these iterations and find the learning rates. And lastly, we plot the graph of learning rate against epochs. So one of the most commonly used learning rate schedules, apart from a constant learning rate strategy, is something called stepwise decay schedules. And with MXNet, if we want to use stepwise decay, one of the first learning rate schedules we could look at is the factor scheduler. And there's a package within MXNet, or a sub-module, and it's LR_scheduler. And you'll find lots of the learning rate schedule functions in this module. So now if we take a look at the code for this one, we first create our schedule, and we're using lrscheduler.factorScheduler. We define the steps and we define a factor. So what the steps is going to do is control the number of iterations before we drop or decay the learning rate. And so this is why it's called stepwise decay. And we're going to decay by a given factor. And so the factor here is 0.5, which means we're going to halve the learning rate every 250 steps. You'll see underneath we set the initial learning rate, and this is called the base learning rate. And so for FactorScheduler, we set it as a property. And this is actually overridden later on, and we'll see, but for visualization purposes, we're just going to set this to 1 so we can see the fractions that we've got over time. And now using that schedule, if we plot over time, we see that we start with a learning rate of 1, then after 250 steps or iterations, we halve the learning rate to 0.5. Another 250 steps and we halve again, and then this process continues. And this will continue indefinitely, getting smaller and smaller. Now, slightly more advanced than the FactorScheduler is the MultiFactorScheduler, and this gives us a little bit more control over to when we do the steps. So as before, we create our scheduler first, and this time we specify step as a list of iterations. So rather than taking a step every 200 iterations, we're now going to take a step after 250 iterations, then 750 iterations, and 900 iterations. That is at 750 rather than 750 more than 250. And we're keeping the factor the same, so we're going to halve when we need to take the step. We set the base learning rate to 1, and then we plot. And we can see now we've got the learning rate going from 1 down to 0.5 after 250 iterations. Then at 750 iterations, we drop again to 0.25, and then we halve again at 900. Now, another form of learning rate schedule that we can use is the polynomial schedule. To access the polynomial schedule, we look at the same module again as before in MXNet.lr_scheduler. And the code for this would look similar to before, where we instantiate a schedule. This time the parameters for the PolyScheduler are max update, base learning rate, and power. So max learning rate specifies the number of iterations before we want to get to 0, a learning rate of 0. The base learning rate, similar to what we saw before, is the initial learning rate, what's defined at iteration number 1. And then the power in this case defines the degrees of the polynomial that we're going to use to interpolate between the starting learning rate and the final learning rate of 0. And here, power of 2 means we're going to use a quadratic function between the two learning rates. Now, if we plot the schedule, we can see a quadratic curve falling from 1 at iteration of 1, and then down to 0 at iteration 1000. So there are 3 implementations in MXNet already, but it's very likely you're going to want to implement your own custom learning rate schedule. And with MXNet, it's really easy to implement your own. So you just need to take a similar form to the functions and classes that we've seen before. So for this example, we're going to implement something called cosine annealing schedule. And this is from a paper called Stochastic Gradient Descent with Restarts. And this is a smooth shape starting from a learning rate down to a lower bound of a learning rate, and it takes the shape of a cosine curve. And so this is just some formula that we could use to determine the learning rate. So what we need to implement is a class, and the class should take the parameters when it is initialized. So here we're going to define the minimum learning rate, the maximum learning rate, and the cycle length. So this is similar to what we've seen before with the other schedulers, where they take in different base learning rates and different steps, etc. This is just what parameterizes your learning rate schedule. So here we're just setting all those properties on self so we can access them later. Then the main method that we need to implement is the call method. So this is a callable class. We instantiate the class and then we can call it just like a function. And with Python, the way to implement a callable class is with the call method. Or more specifically, we have underscore, underscore call, and then underscore, underscore. What MXNet expects is to be able to pass an iteration. So this is the iteration that we're going to be on through training. And then the function will return the learning rate to be used for that iteration. So here, if we pass an iteration, we're going to go through the logic and do our returns. So what we're looking at here is if the iteration is before the cycle length, then return the learning rate as per the cosine annealing schedule. And if it's beyond the cycle length, then just return the minimum learning rate. So this is going to do an annealing, and then it's going to stay constant at the minimum learning rate. So let's take a look at what this would look like now that we've implemented the class. We instantiate the class or the schedule. We give the parameters that we require. So we're going to have a minimum learning rate of 0, a maximum learning rate of 1, and we're going to do this across 1,000 cycles. So we could implement this however we wish, as long as we get this class that's been instantiated. Now we give that to the plot schedule, and remember our plot schedule function called the schedule at every iteration between 0 and 1,500, so we can get an idea of what the learning rates will be over time. And here we see a cosine curve between 1 and 0, and then we maintain the minimum learning rate value, which in this case was 0 thereafter. So if we provide iteration values greater than 1,000, we just give 0. And so this was an example of how you can implement your own custom learning rate schedules for training. So now let's move on to the most important part. Once we've defined our schedules and we're happy with the schedule, now how do we actually use that as part of training? So we could manually change and set the learning rate over time, but there's actually embedded functionality within MXNet to use learning rate schedules as part of training. So let's take a look at those now. We're going to use an example neural network model for this, for demonstration purposes, and we're going to train on the MNIST dataset, so handwritten digit recognition. So here we're just specifying what context we're going to use and defining the dataset and the data loader. Next, we define a simple convolutional neural network with a number of convolutional layers. And we initialize our network and define a loss. So this is all very typical for what we'd be doing when training our own neural networks. So as mentioned before, we could define a schedule based on an epoch or an iteration. But for MXNet, the way it's used, it expects it to be defined for iterations. So if we wanted to change the learning rate at certain epochs, let's say we wanted to drop the learning rate and have a stepwise decay schedule where the drops were at epochs 4, 7 and 9, we need to convert that to iteration numbers before we use these schedules. So let's run through the maths and how we do the conversion. So now we know the epochs that we want to take the steps. We need to find out how many iterations there are per epoch. Now this depends on the size of the data set and also the batch size. So the way we find the size of the data set is we can call the length of the data set. So here we're doing len train data set. That's going to give us how many samples there are in the training data set. And then we want to divide by the batch size. So this is going to give us the number of batches that we're going to have to go through before we've run through the whole data set. And we just round up to be sure. And this is assuming that we use the keep the partial batches, which is defined by the last batch parameter of data loader. And this will say how many iterations we have per epoch. Now that we've got the iterations per epoch, we can scale up the steps that we had defined in epochs to find when we should take steps for iterations. And by running that through, we can times the step by the iterations per epoch. And now we have the steps defined in terms of the iterations. Now that we have our steps defined in iterations, we can go ahead and create our learning rate schedule. So here we're going to use MultiFactorScheduler because we have uneven spaces between our steps. And we pass the steps through with the step parameter. And our factor in this case is 0.1. So we're looking to reduce the learning rate by 90% or have the value be 1/10 of what it was previously. Now this is the most important part. Now that we've got a schedule, we need to give it to the optimizer. So whenever we define the optimizer, we want to pass an LR scheduler. So we set LR scheduler equal to the schedule that we've already instantiated. The learning rate, where we set that in the optimizer, that will override the base learning rate of the schedule in the case of MultiFactorScheduler. When we saw MultiFactorScheduler previously, you'd remember that I'd set the property of base LR to 1, just for demonstration purposes. Here, the optimizer will handle that for us and set the base learning rate to 0.03 in this case. If we define our own custom learning rate schedules that don't take or use the base learning rate, then they'll carry on using the learning rate that is returned by the call method, rather than using the learning rate specified here. And this is now pretty typical from here onwards, where we give the optimizer to the trainer. So whenever we take steps for the trainer, it's going to do one extra iteration, find out the right learning rate to use based on the schedule, and then take the step. So it's all going to be handled for us. We just needed to pass the schedule to the optimizer. The example here is for Gluon, but if you were using Module API, you could use the optimizer with the learning rate schedule as part of the module. So it's not just specific for Gluon. So after this, we have the typical training loop. Here we're iterating through batches of our data. We're going to do the forward pass, do the backward pass, and then we're going to take our step with trainer.step. So it's when we call trainer.step that it's going to use the optimizer and the learning rate scheduler we've defined to find out the next learning rate to use for the next iteration, and then use that learning rate for the step that's going to be taken. So there is another method for setting learning rates and using learning rate schedules, but this is much more manual than we've seen before. Before, everything was handled automatically by the optimizer and the trainer, but in this case we're going to manually use the schedule and manually set the learning rates. And this is used for Gluon only. So for this example, we're going to create our neural network again. We're going to initialize the parameters, and we're going to redefine our schedule. So we're using the same step iterations as before with the same factor. But because we're not using the optimizer to do and manage the schedule for us, we have to manually set the base learning rate as we did with the plots. So we're setting schedule.baseLR to 0.03. And then we initialize our optimizer, and you'll notice we haven't passed the schedule at this point or set the learning rate. This is going to be managed completely independently. We create the trainer, passing the optimizer. Again, at this stage, the trainer has no awareness that there is a schedule that's going to be used. We iterate through the data, and we have batches of data. Before we take the trainer step, we want to work out what the learning rate should be. We're going to set the learning rate of the trainer, and then we're going to take the step. And so we can see that in this part of the code. We call our schedule with the iteration index that we're on, and we're keeping a record of the iteration that we're on. So we start with an iteration of 1, and then as we loop through, you'll see we have an increment of the iteration after we take every single iteration and batch. So using this iteration index, whatever value it's on, we find out the correct learning rate to use for that specific iteration. Then we set the learning rate of the trainer. So that's going to actually set the optimizer within the trainer, and we pass it the learning rate that we've determined is the correct value to use. And now with the learning rate set, we can take our trainer step and then continue the process. So this is a more manual procedure. It's not handled automatically, but could be used if you wanted to take some kind of feedback mechanism and change the learning rate based on what you're getting back in terms of the loss. In the next video, we're going to be implementing a number of state-of-the-art learning rate schedules to help you train your models much quicker and get better performance.